Hello everyone. Today lecture. From this lecture, I'll introduce the concept of the measure theory. But to understand why we study measure, I'll introduce some problem of the Riemann integral, or limit of the Riemann integral. To understand this, from the lecture 12, I will introduce the definition of the Riemann integral and its property. And then the next lecture, I'll introduce the limitation of the Riemann integral and why we should introduce a new method of the integral. This is the Riemann integral. And to understand the Riemann integral, it is essential to understand the measure theory. Anyway, in this lecture 12 and the next lecture, I focus the Riemann integral. Let's recall the concept of the Riemann integral, but the Riemann integral is so familiar when we study in the elementary calculus. We evaluate this integral. But I some more detailedly define and introduce the concept of the Riemann integral. Anyway, let's start the definition of the Riemann integral. The idea of integral is clear. If we evaluate in this case, because fx is a positive, if we find the area surrounding this graph, y is equal to fx, and x is equal to a and x is equal to b, which is perpendicular x-axis, and this either convenience put a, we know to find the area A is integral from A to B fx dx. If we find the nice function fx is given, we can find antiderivative function, and fundamental calculus of theoretism, we can evaluate this area. But to see the original idea of Riemann integral, if we does not know the fundamental of the calculus theoretism, if we just find the area without FTC, the primitive method is this area is part easily understand to evaluate area. For example, this is not square, this is not, because this is not square, this is not triangle. We can use any formula. We cannot use any formula to evaluate this. But if we consider this area is partitioned into the rectangular, but if we consider this rectangular, this occurs the error term in this part. So to keep the problem, we can finally partition the area, and if we calculate this area, because we know the area of rectangle is length times height, okay? So we can just evaluate this area. But if the area, the partition is larger, this clearly error between the rectangle and the area. But I say refine partition partition finally, this means technical means taking the limit. Okay, we can approach the converge, this rectangle converges to area. Then when it comes to when it comes to consider the partition of the rectangular area, we can consider how to partition this. This means we first consider this point. We first define the partition point this area. So we originally, traditionally, this is the 0 part, x0, and this is x1, and this is x2. But important point is that the partition, even though the calculation is a little complicated, the partition, if we partition this rectangle, the length of the rectangle, this is the height, this is the length. This length is not uniform on other rectangle. So this is bigger than the previous and thinner than the previous. Okay? Anyway, we can define such partition. Repeatedly, we carried this task repeatedly. Arbitrary part of the area is xi and xi plus 1, and the final part, if we approach the final part of this area, this is defined xn, and this part is xn minus 1. And we can define the partition, which depends on this parted to depend on the rectangular's length. To define is just define xi plus 1. Okay, this where the notation is the a is the x0 in this part, x0 is a, and n is the b, and x0, x1, xn. Or is this rule regulated? Then this is the partition. Just partition, literally the height, the length of the area, the length of the rectangle. And obviously, if the element, this consists of element of the interval, but the element, more element exists. This means the more finer the area, which means the more approach to area A. This gap, which is exceed the area A, the gap which difference from the area A is reduced when the number of the partition is increasing. Okay. And I forget some another notation, delta x I. Delta xi means just define the length of each rectangle. So define is xi minus xi minus 1. So if we just think this, rather than if this part is xi and this is x minus 1, the length of the rectangular is xi part. Okay. And okay, in each rectangular, the length is defined here, and the length is, I said, the arbitrary. Okay. And how to define height, which corresponds to this here? The method is many ways. Check the maximum value, those is no problem, and the minimum value is no problem. And some others define the average of this area. So this is the maximum and this is the minimum, and height define this average value of minimum and maximum. Anyway, the method to take the height is no special rule, but in this case, the calculation and more the bizarre if we take a more bizarre method, the calculation is very complicated. So, and when considering the concept of the Riemann integral, the main method how to take the height of the rectangle is two methods when considering our theme, Riemann integral. This is the upper sum and the lower sum. Let's consider this here. Upper sum is we might guess this height as the maximum value of this area. But some technical problem many people define rather than the supremum value rather than the maximum problem. Of course, suppose in this case, suppose if f is the continuous function, and then when considering this interval, because this is closed and bounded function, this is clearly compact. Compact set in given fx is a continuous function and the function is to define the compact set, clearly the maximum value and the minimum value is clearly exist. In this case, this is the maximum part and this is the minimum part. Then upper sum method is absolutely we take the maximum value as the height. Take the maximum value as the height of the rectangle. So in arbitrary case, this is the maximum value here. But I said if this function is continuous function, supreme value of the interval fxi given the where in this case supreme fxk fxk where xk is contained xk minus 1 xk in this case is same as the maximum value of this interval. Later I'll introduce why the supreme value is the better definition rather than the maximum. In this case, it's the same. So we can take the maximum or supremum instead of maximum. Instead of supremum, we can take this maximum if the function is continuous function. So anyway, if I will define this function is the mxk. Don't misunderstand. This is anyway the technical problem. I will in this case I define the supreme value. In this put mxk rather than the maximum. So in arbitrary case, take the supreme part of this interval, take the height of the rectangular, and the length is already defined delta xk. And this is arbitrary part repeatedly carried in each rectangular. K is, in this case, K is 1 to n. This is the upper sum of the rectangular. And in a similar way, we can define the lower sum. In case of the supreme, in case of the upper sum, take the supreme value. The lower sum take infimum value. fxk, where xk is contained xk minus 1 xk. Of course, if the function is continuous, we can also check infimum. Infimum is same as the minimum value. But I said the technical problem, we can define infimum is the definition of the lower sum. So in this case, the lower sum is the clearly each area is smaller than the upper part. Okay, in this case is here, and in this case here, take the lower sum. And we can define this value in each interval. Clearly the value exists, then this value is small m xk. So in a similar way, we can define the lower sum is from k1 to n m xk delta x. Okay. Then if we find the upper sum and the lower sum each part. But this is clearly the difference, the area we want to get, because this has clearly gap. In case of the upper sum is larger than the area A, and the lower sum is clearly smaller than the area A. But as I said, if the number of the partition is increased, we clearly this value is approaching the area A. So in this case, because this is the larger than erase this area, so take the limit. This is case of the area. Okay, this is the number. So in this case, because this is always larger than A, take the lower limit of the integral. So this take the lower limit of the integral, and take the upper limit in case of this. Take the upper limit of the integral. Then I deleted this part here, so there was space. we can remarkable these two value. First, this part. Some others, this define infimum upper sum f, and this value is defined the minus 0, 1. If we define the fxab, okay, a from a to b fx dx. Is this? And this case, some others define supreme upper sum, a supreme lower sum. So, because when this here, UPF is larger than the area A, if we find the value of the A, this is the infimum of the value, and in case of the lower upper sum, take the supremum of this area. Then the area is clearly approach A we desire, and this is defined. It's defined from A, B, Fx. Okay, the definition is here. And if we try to this lower upper sum and the lower sum, clearly the area is clearly approach the A. Indeed, if this value first, if this value and this value exist same as clearly the A, then we can define the A is defined A from AB to fx dx. So if the integral value exists, means the lower sum, this sum and this integral is clearly same value. Okay, and we can define then second, if the value is important, if the value a, b, fx, dx clearly exists, then we can say f is Riemann integrable, but literally can be able to integrable in the Riemann sense, and this is usually said f is contained Riemann sum R A B. The remarkable theorem we should see is this theorem. Statement A is very clear statement. In others, this means f is continuous. It implies f is contained Riemann integrable. This means just roughly speaking, there exists the integral. The value integral from a to b f is the value exists in the real number. So, for example, easy example, if fx is the exponential function is clearly continuous function. not only in the specific, not only the whole real number, but also a specific interval. Okay, so if we consider, for example, 0, 1 ex dx e to the x dx, but in this case we studied by fundamental theorems of the calculus. Okay, this is easier to calculate the integral, but to find anti-derivative, but exponential anti-derivative of the exponential function is still still exponential. So this is the result is exponential minus 1. Okay, so this is clearly exists real value as a real value. Okay. The interesting theorem is the second property. Suppose f is the monotone in AB. What is the monotone? Monotone means two meanings. In this case, monotone increasing altogether. The monotone increasing and the monotone decreasing. All together, we say monotone function. The definition of the monotone increasing is here. This is so narrow, I use this here. Okay. If x, consider x, y in the given interval AB, then the definition monotone increasing means if x is smaller than y, then fx is smaller, or including the equality. Okay, fx is smaller or equal to fy. The remarkable point is contained equality. Okay, this equality is contained. If this is vanished, we can say this is strictly increasing. Strictly increasing if fx just smaller than fy. And in the same rule, we can define the decreasing case. If x is smaller than y, in this case, the inequality is flipped. So this is monotone decreasing. Also, if in this case, if we if the equality vanished, we can say strictly decreasing function. Anyway, in this case altogether, we define monotone function. Then, if the function is the monotone, then this is still Riemann integrable. This means there exists also the value from integral from a to b, the given monotone function. So we intuitively understand the increasing function. For example, I just understand, did not delete. Considering this function, this exponential is clearly a monotone increasing function. This is clear by the definition of the monotone function, and just drawing the function. Intuitively, we check this is integral function, increasing function. So the increasing function clearly, this is also seems to be clear theorem, as looks like the statement A. So, but the problem is occur when considering this graph. I deleted some text, and let's watch such example. This is the well-known function. Usually this notation is expressed special bracket. x. This is called Gauss function. The definition of the Gauss function means if a is the number, okay, x, just x, this is clearly the real number. So if x is chosen, there exists x is clearly larger than, including equality, a, and smaller than a plus 1. So this is clearly integer part. If the x is given, the integer part is a. So just roughly speaking, a point xxx. Then the Gauss function spew out just integer, its integer value, spew out integer value. So this is Gauss function. So for example, by using this graph, if we calculate for example 1.6, this is evaluate 1, okay, and if we consider minus square 3, this is this is clearly, in this case is clearly this here, okay, this value spew out 1, and minus root 3 is clearly this point, okay, this spew out minus 2. So this is the Gauss function, but I suggest some integral. This is the integrable from minus 2 minus 1 f, or from minus 2 to 1 f. This is integrable. Is this integrable? The answer by rendering this theorem B, yes, this is clearly exist, because just depending on this theorem, this Gauss function is clearly monotone increasing function. If we choose this value x and y, in a different case, this is clearly fx, the value fx is smaller than fy. This is minus 2, this is minus 1. And even though we can choose this same point, y and y prime, again, the definition of the monotone function is clearly including the equality. So if this equation satisfied, y prime, this is y prime, this is y. So anyway, the Gauss function is monotone increasing function. So by using this theorem, this value is clearly exist. If we calculate minus 2 from minus 2 minus 1 to integral f, the main problem is here. Even though this is integral is clearly exist by giving the theorem, and this Gauss function is monotone function, this point x minus 1, the function, Gauss function, is discontinuous function. This is clear. The left limit and the right limit is not coincide. So this is no problem to evaluate the value. But note that if the value, the existence of the value means the lower sum minus to 1 f, and the upper sum to value is the coincide. So even though regardless of the discontinuous or continuous, if anyway the value is the coincide, this f is Riemann integrable. Okay, then to check, I'll check this equality of the integral. To calculate this integral, first the left side, and I deleted some here. Okay, the LHS left side, to begin it, I calculate the upper sum UPF, where is F is the Gauss function, P is the partition. Then the upper sum, in this case, the upper sum, okay, to begin it, the partition defined uniformly same, so X or Xi to be uniform, minus 1, minus 2 of n. So the result is n over 1. So all of the interval, all of the rectangles, even though this is negative part, this is not can be the area, but we can just understand each rectangular is correspond to here, but each interval is always same, okay? Not bigger, thinner, just same as all of the part. Okay. Then, and the definition of the upper sum is the take the this case k to 1 and the supreme value of the each height is supreme value, where mk is a supreme if xk is the element of the star to describe xi plus 1, okay, and delta x, but delta x is always n over 1. And take the each step, each interval, minus 2, 1, take the supreme value, but this is negative, note that this is negative part, and each part except from the last part, this here, always the mxk is minus 2. Okay? The problem, of course, this here. The last partition, for convenience, I put this x n minus 1, and minus 1 is 2xn. In case of the last interval, from xn minus 1, xn minus 1, xn, each element is given, okay, but consider the supreme part of this interval, this here, the value is minus 1. So the last rectangle is changed here. If we calculate the upper sum here, then we can participate k from 1 to n minus 1, mxk n over 1. The last part is here. So the last part is minus n over 1. And we can directly calculate this here. Every value is the minus 2. Minus 2, minus 2, minus 2. So the lower sum is n2, but the term is total n minus 1. And n minus 1. So the result is n of 2n minus n of 2n plus 1. Okay. And we can take the upper sum. This is just the UPF. Then if we take the infimum of the value, this clearly goes to minus 2. And in case of the lower sum, we can calculate same way here, but this takes the infimum value. So this is same when you calculate as same rule in the first and second, third, so here, but the problem occurs the last part. Okay. In this case, we define whether in the blue case is here is the last part of this sum, but in this case, this point is the lower limit sum, because we can take the infimum value when you consider small mxk, okay, small mx n star when consider xn star is contained xn minus 1 xn means minus 1. The such value here, we pick this point here or here, this is the correspond to infimum part. In similar way, we can direct the definition of the lower sum. If we calculate the area, the calculation is directly calculate. This is all of the area is the same from k to n minus n over 2 n. Okay, this is it's directly calculation. N minus 1, this minus 2, and this is n terms. The partition is the n partition. Okay, so this is just minus 2. And this value is minus 2 as we take the supreme of this area. So, because this two value is the same, we can say this value is exist. So even though this point is not continuous, x minus 1 is not continuous function, regardless of the continuity, the value of the existence depends on the lower limit and the existence coincidence of this value. And if we calculate, for example, minus 2 f, in this case, we can part each area. Minus 2, 1, f, minus 1, 0, f, 0, 1, f, and 1, 2, f. And each value is clearly well defined. For example, we show this value is clearly existed by the lower limit and upper limit is the coincide. Similar way, we can check this and this is also well defined. So by property of the integral, we can part each area and we can calculate this. This is minus 2. This is minus 1. Just this here looks like multiply this length and this length. This is 0. And this is 1. So this value is minus 2. So when considering this point, even though when I calculate the range 2 from minus 2 to 2, so here, okay, even though remarkable point is even though this part and this part and this part is clearly, each point is discontinuous, okay? Even though this continuous function, however, we can evaluate the value from minus 2 to 2.